Good day, everyone, and welcome to today's webinar titled Introduction to EPA's Stormwater Management Model, known as SWMM. This webinar is sponsored by EPA's Water Modeling Work Group. I'm Tim Wool with EPA Region 4 in Atlanta, Georgia, and I'll be moderating today's webinar. Thank you all for joining us today. First, I'm going to briefly summarize some of the features of today's webinar. We hope everyone will have a lot of questions today. The phone lines will not be open, but you can type your questions in the question box and click the send icon. If you have problems viewing the broadcast, just let us know in the same questions box and we'll post an answer in that same box. This webinar will be archived for later viewing on EPA's Water Modeling Workgroup page, and we will provide the archive link for you on a slide at the end of the webinar. Also, at the end of today's webinar, you will be able to obtain a certificate of attendance for participating, and we'll provide directions for downloading it at that time. Lastly, the materials in this webinar have been reviewed by EPA staff for technical accuracy. However, the views of the speakers are their own and do not necessarily reflect those of EPA. Mention of commercial enterprises, products, or publications does not mean that EPA endorses them. Now that we've covered the logistics, I'd like to provide a quick introduction to this webinar series. I would like to remind everyone that this webinar is one part of a webinar series that has been going on for the past 2 years. The purpose of this webinar series is to help water quality professionals better understand water quality modeling and how models can be used to solve the problems facing water quality regulators. Today's webinar is the 14th in our webinar series. All of the past webinars have been recorded, archived, and posted to EPA's YouTube channel website. Links to the archive files are available on the Modeling Workgroup website. The link is at the bottom of this slide. In a few weeks, an archive of today's webinar will be posted on the same website. Because this is a webinar series, we encourage you to go back and listen to some of those previous webinars. If you haven't already, they do build on one another, starting with modeling basics and moves up to the more advanced topics we're talking about today. These webinars are targeted to water quality professionals who may use, want to use, or review models as part of their job, but who do not necessarily have modeling background. As such, we are assuming that you have basic understanding of water quality science and concepts, but perhaps have limited direct modeling experience. And with that, I'd like to introduce today's speaker. Today's speaker is Dr. Michelle Simon. Michelle is a chemical engineer and the Associate Director of Science and Water Systems Division at EPA's National Risk Management Research Laboratory, which is an office and research and development laboratory in Cincinnati, Ohio. She has over 20 years of Superfund site technical support and has just recently taken over as EPA's lead for the SWMM model from Lou Rossman, who retired from EPA. With that, I'd like to hand this over to Michelle.
Hi, Tim. Thank you for that nice introduction, and thank you, everybody, for coming to this webinar. I'm really astonished at the turnout. And I do want to say that I am a chemical engineer. I am with EPA in Cincinnati. I took over from Lou Rossman, and EPA lost a lot with the retirement of Lou Rossman. For the last 17 years, he has refactored SWMM 4 and SWMM 5. There's 45,000 lines of code. He has written each and every one of them with input from several members of the community like CDM Smith, University of Florida, University of Oregon, so a lot of really good insight. Fortunately for me, he has been working, and fortunately, frankly, for all of us, he's been working in the emeritus position, and he is still very active on the SWMM listserv, and we are lucky to continue to have his expertise as we move forward. I, for one, find it very reassuring. Alrighty, Tim said the disclaimer. It's kind of disconcerting when you are an EPA person and the first thing you have to tell everybody is all opinions expressed in this presentation or those of the author are not necessarily reflect the views of the agency. But one of my reviewers said that I do need to highlight that any mention of trade names or commercial products does not constitute endorsement or recommendation for use. I'm indebted to several of the commercial vendors that sell SWM, primarily Bob Dickinson of Innovise and Rob James of CHI Water. I've used some of their slides and I've benefited from many helpful conversations with them. There are other vendors of SWM and contractors who work with SWM, and they also are very much, in their opinions and insights, have been very welcomed as well. I also should highlight that I've used some slides from Lou Rossman and others from Jason Vengeros, and I will highlight those when I hit them. Alrighty, I'm going to talk about SWM. This is an introduction to SWM. I'm going to talk about the processes modeled by SWM, give a quick demonstration of a very easy project with SWM, talk about low impact development or green engineering, National Stormwater Calculator, give you some websites on how to locate the data, talk about where you can get some technical support, and then have a couple of sessions, a couple of breaks in the presentation to talk about questions. This is only 45 minutes. We could spend months talking about SWM, so I'm going to highlight what I think are the most commonly used aspects of SWM. I appreciate Tim inviting me to give this talk, as well as Jason Gilday. Jason wasn't able to be with us today, but he has gone through the slides, and he specifically asked me to talk about SWM, HSPF, SWAT, and WASP. I understand that HSPF, SWAT, and WASP were the three talks before mine. SWAT, Stormwater Assessment Tool, is from the USDA. It's available from Texas A&M. It's designed to do watershed modeling and nutrient runoff primarily for agricultural sites. It does a very good job of evapotranspiration for a field of corn, a field of wheat, a field of soybeans, and so on. It is an excellent model. It's been out there for many years, and it's very widely used. As is HSPF, Hydrological Simulation Program in Fortran. There's some others that are in C and in Python. It is a good general. HSPF is a very good general watershed model, and I'm sure many of you use it to calculate TMDLs and other regulatory values. WASP, in fact, Tim is the expert here on WASP, and it's a water column model. It's designed for aquatic systems and the underlying benthos. SWM is used, it's a stormwater management model. It's used for urban environments. It's important to have a model designed for urban environments because urban environments change what the natural watershed model would be. When you urbanize a system in the beginning, up here on the upper left-hand side, where there's no urban or man-made structures, of an inch of rain, 40% of it evapotranspirates, 10% may run off, 25% is available for plants for shallow infiltration, and 25% could go into the groundwater. As you become more and more urban, you have more and more impermeable area that the rain falls upon, and less plants. You do have more, you can typically have a lot more temperature, and you can have a lot of evapotranspiration, but instead of infiltrating, you get a lot more runoff, which gives you a lot less for shallow infiltration and even less for groundwater. Stormwater impacts, when you think of the urban environment, you think of stormwater running off from it. You have increased volume and increased velocity. The velocity can cause flooding, erosion, and sewer overflows. In fact, we're experiencing that right here, right today, here in Cincinnati. We have a lot of flooding. We have some flooding from the Ohio River and other streams that are in Cincinnati, the Cincinnati area. As water moves through the urban environment, it picks up metals, PAHs, and if it has combined sewer overflows and other terrible things, it damages the aquatic environment and the surface water bodies. This is the primary cause for surface water infringement and for beach closings and for drinking water alerts. In addition to the fact that we have more runoff, we have less groundwater recharge, and this is a huge area, particularly in the Southwest, where they have a lot of flat land, they have a lot of runoff, and they are desperate to have more groundwater recharge. SWM models the urban environment. SWM is a public domain, open source, distributed, dynamic hydrologic, hydraulic water quality model that is used for continuous simulation of runoff quantity and quality for primarily urban areas. It is written in C. It has a Delphi graphical user interface. It is a solid piece of software. It is robust, intuitive, and easy to use. What does SWM model? Okay, up here, you have an area. Rain falls down onto the area. Some of the rain transpires, some of it infiltrates, but lots more of it runs off. As it runs off, it can go into streams, it can go into culverts, it can go into the man-made sewer environment. As if you have a combined sewer system, and I don't know if lots of folks here work with consent decrees, you can have a lot of trouble with combined sewer overflows impacting surface water bodies. SWM is probably the best hydraulic watershed model out there. It does a lot of modeling for junctions, conduits, pumps, storage tanks, orifices, weirs. The typical thing one would do is you have stormwater running into an urban environment. You calculate how you can design the sewer shed flow. The typical point of dependent variable is the outfall. How much runoff do you have that's getting into either your wastewater treatment plant or your surface water? SWM is used for the design and sizing of drainage system components, the control of combined and sanitary sewer overflows. It models inflow and infiltration into the sanitary sewer system, generates non-point source pollutant loadings for load allocation studies, evaluates green infrastructure for sustainability goals, and can do floodplain mapping for natural channel systems. SWM is, we accept a lot of consent decree designs for urban water infrastructure upgrades based on the results of SWM or some of SWM's commercial compounds. SWM is generated by the government, is open source, free, and able to be downloaded. XP SWM, PC SWM, Info SWM, there's a lot of vendors out there that have put very interesting wrappers around SWM, but SWM is primarily the engine for most commercial products. Let's see. Here's SWM's conceptual model. SWM is modeling rain, so you need a rain gauge and you need precipitation data as well as evapotranspiration data based on temperature and wind speed. You also need sub-catchment areas. Rain is a length. Sub-catchment areas are length squared, so combine their L cubed flow. You have flow that comes from your sub-catchment area into a node, into your conduit, into the rest of your sewer system. SWM is used for billions of dollars of upgrades for multi-decades worth of work. The idealized sub-catchment, and I want to highlight, I got this slide from CHI Water. You have the sub-catchments, and you want to have uniform characteristics of the sub-catchment. It is an area interpreting, it is an area that is intercepting your storm water. The trick of SWM is to figure out how to subdivide your sub-catchment. Do you want one big sub-catchment or a bunch of smaller subdivided sub-catchments? The sub-catchment has to have uniform properties. If you have one big one, you gain a lot of computational time. If you have a bunch of small ones, you can end up having a better representation of the physical reality of your fluid mechanics, but you end up having a more complex system. There's a very nice YouTube video that is produced by CHI Water that I recommend you take a look at for some more on this issue. The governing equations are the depth of rain or water onto a subcatchment is a function of either the rainfall of the snowmelt minus the evaporation minus the infiltration minus the runoff. Pretty simple, pretty basic. One of the nice things about SWM is it's very robust and intuitive. SWM has governed by continuity. And the continuity is in the storage, in the nodes, and in the storage units. And in the conservation of momentum, you figure out the momentum in the conduits and the culverts and in the conveyance things. For momentum, you have the change in flow with time is equal to the dynamic wave aspects of the flow, the drop in head, and the friction slope. SWM assumes that you have varied unsteady flow. It's used the St. Bennett equations, and it has 3 different levels of sophistication. One is steady flow routing, no change with time. Another is kinematic wave routing, and the third is dynamic wave routing. it is usually recommended to use dynamic wave. Dynamic wave is unsteady, gradually varied, open channel flow, whereas kinematic wave is uniform and it uses the Manning formula. And it's a steeper wave with less dispersion and attenuation. Dynamic wave routing is used for branched or loop networks. It handles backwater, the flow of a bathtub, flow sloshing back and forth. It's free surface flow. It can handle pressure flow and surcharge. We have a lot of open channel flow, but we also can have force main flow handled in SWM, and it can do flow reversals, which can happen in a loop system. Kinematic wave, while somewhat more intuitive, cannot have loop networks and cannot have backwater effects and cannot handle pressure flow. Another very nice YouTube video that I recommend you go to if you're not familiar is one that I believe was done by Bob Dickinson. In addition to flow through channels, conduits, pumps, and pipes, SWM can do pollutant buildup and wash off onto a sub-catchment. For a sub-catchment, without the rain, you can get pollutant buildup and wash off onto the sub-catchment when there is no rain. But when there is rain, you can get flow onto the sub-catchment with a concentration of contamination. You can have runoff from upstream sub-catchments and other areas with their concentration. You have evaporation, you have infiltration with the concentration of the ponded value. Together, these come up to the contaminant wash-off from the sub-catchment. Recently, since 2010, SWM has been able to model green infrastructure. Green infrastructure, the purpose of green infrastructure, and I'm sure most people here are quite familiar with it, was rather than having a lot of runoff from urban environments, what if we put in more green infrastructure? What if we put in more natural type systems that allowed for more infiltration close to where the rain falls, so there's less time to pick up contaminant and more time to move through the subsurface and recharge the groundwater and be available to plants. So this is a representation in SWM of a bioretention. We have 3 layers, surface, soil, and storage layer. You have runoff from upgradient and infiltration from the surface layer into the soil layer, into the storage layer, into the subsurface. You could have an underdrain, you could have overflow, and again we have the rainfall directly onto the LID and evapotranspiration out of it. There are various different types of green infrastructure sub-catchments, such as green roof, roof disconnection, permeable pavement, vegetative swells, and some others. Green infrastructure is just there's gray infrastructure, pumps, pipes, takes. There's green infrastructure, LIDs, low impact development, SCM, storm control measures, DUDs, distributed urban design, BMPs, best management practice. There's a family of practices that are enveloped within green infrastructure. SWM is one of the first models. I think other models such as SWAT and Kineros are trying to put green infrastructure into their software. We have recommended to them and are in communication with several of them, and they're looking at trying to interface with SWM LIDs so they don't have to do the modeling themselves. So with that, I'll pause for the first batch of questions.
Okay, Michelle, we only have right now only 2 questions. The first one is, what is the smallest area that you can accurately model with SWM?
We can model something like 0.1 acre. Well, in terms of sub-catchment, we can model 0.1 acres, at least we do with the stormwater calculator. We can do hundreds of acres with SWM. I don't know that we have a small area per se. I guess if you would take a pail and try to model it, you should be able to do it with SWM. As far as I know, there's no limitation.
Okay, and then the next question someone's asking is, can it handle a small agricultural sub-watershed within its network?
Well, it can. In fact, we have a project. Chris Neach, my colleague here in Cincinnati, took a watershed, like a Hut 12 watershed, and at first he modeled it with SWAT, and it was an agricultural watershed. And through the years, they started building a McMansion subdivision, which he modeled with SWM. And then he and his colleagues are working on interfacing SWM and SWAT. SWAT, the USDA product, would be a better, is designed for agricultural. Now, if you had good values for evapotranspiration, you could probably use SWM, and it probably would do a good job, and it would be interesting to try. So why don't you drop me a note, whoever asked that question, and we can talk some more about it.
Great.
The problem with SWM isn't being small. The problem could become being large. But in general, SWM should do a good job, provided you had good evapotranspiration values. If you do not, then I would advise you to use SWAT for the agricultural portion of it.
Okay, next question is in regards to modeling nutrients within SWM. How good is it for doing phosphorus and nitrogen?
Well, it has a very rudimentary contaminant buildup and wash off approach. I think that SWAT again would probably be better with nutrient runoff, and in fact that's one of the things that we're looking at with Chris Nietzsche's project, is how well it does nutrient runoff. There's a very good, if you go to the SWAT webpage, you see some really good papers about the calibration of SWAT with nutrient runoff versus various different fields. SWM does not do evapotranspiration as well as SWAT, and it has a fairly, rudimentary approach for contaminant buildup and wash up. And that's actually one of the research areas of mine, is to validate and to test how well SWM does various things. Okay, this next question, can SWM model an inverted siphon, which I'm going to have to figure out what it is later. I'm afraid I'm going to have to, it's funny, an inverted siphon, that's pretty cool. You know, I don't know. I will give it a go after this. Frankly, that's the first time anyone's ever asked that question. But I do remember that from the PE exam, the inverted siphon. So I'll check it out. Okay, what tools are being developed to assist in reporting the results for SWM? Okay, well, there are some good tools. First of all, later on in the talk, I'm going to talk about open SWM, and one of the things that I think the commercial vendors do extremely well is put wraparound SWM, and so that it's a lot easier to calibrate SWM, to evaluate the results, and to present the results. As far as wraparound, there also is, and I'll give a shout out to another one of the vendors, even though I'm not endorsing anyone in particular, is a man named Bryant McDowell, has an API toolbox in which one could interface SWM with other types of interfaces in order to get better results. As far as, I think basins you can use SWM. The SWM that I thought I saw in basins was SWM 4. We're up to SWM 5.1.0112, released last year in March. And I don't know how well basins itself interfaces with SWM. I am talking to the folks that do AGWA, USDA, and Arid Lands Research or whatever, Arid Resources, I forget who they are, but USDA was looking at adding LIDs to their interface, and I suggested to them that they interface with SWM, and I'll let everybody know how that goes. Great. Another question is, tree canopy considered a green infrastructure practice, or is it factored into other practices? This is another area that we'd love to add to SWM, and we don't. And that's a common observation from reviewers of SWM, is that they'd like to add tree canopy. We're looking at iTree from U.S. Forestry. At the moment, we do a rudimentary job on evapotranspiration, and we don't look as carefully at agricultural evapotranspiration the way SWAT does. One of the things that I'm the PAL for SSWR, Safe and Sustainable Water Resources, and we're looking at green infrastructures. And there's a lot of models out there, and rather than trying to add stuff into SWM, my co-PAL Steve Kramer and I have looked at various different models and see where we could interface SWM. So rather than adding the feature to SWM, we added the capability for a person to model what they need to model, and we take advantage of iTree and SWAT and Caneros and ModFlow and other models that other people are doing in the public domain and well. Okay, thanks. Another question is,
Can SWM model sediment transport?
SWM has the build-up wash-up for sediment transport. SWM does not try to do surface water sediment transport or anything in the subsurface. I had thought about adding sediment transport to SWM, and what I've decided to do is look at the way HSPF does sediment transport and see how it can interface SWM to that.
Okay. Another question, does SWM use curve numbers as part of its calculations?
Yes, it does, and when I demonstrate SWM, I'll show you how. And in fact, if you want to, I can go to the SWM demonstration. We'll have some more time for questions at the end.
Yeah, let's go ahead and do that.
Okay. So anyway, I'm going to walk you through SWM. I'm going to do a really simple example. I'm going to talk about the hydrology of SWM, the sub-catchments and the LIDs. I'm going to talk about the hydraulics, water quality, and I'm going to talk a little bit about the calibration of SWM. And with that, we'll head to SWM. Let's see, I hope this works. Okay, this is SWM. Later, I'll show you how to download SWM onto your computer if you don't have it. SWM is an intuitive, robust model. It very rarely breaks down. It's a fairly dependable model. At the bottom of our slide, we'll start in auto length. I'm going to turn it on. You can turn it on or you can turn it off. SWM is not an add-in into ArcGIS. SWM has its own independent graphical user interface. It is not as robust as ArcGIS. In fact, a lot of my projects, I figure out lengths and areas and so on with an ArcGIS model, and then I take the model and I put it into SWM, and I'll show you how. We can either work off depth or elevation. I'm going to stick with depth. You can use English or metric units. And you start a project. You do the defaults. You go, I'm going to just put in a rudimentary nomenclature and show you how it's done. And then I'm going to have default sub-catchment and default node lengths. You have an area, you have a width. The area is 5 times the width, percent slope, percent impermeable. Let's say I'm going to say 50% of my sub-catchments are impermeable. If I want to adjust this sub-catchment by sub-catchment later, I can. I have the Manning's N for impermeable, Manning's M for permeable, D-storage for impermeable porage, and percent 0 for impermeable. As you go through different sub-catchments, it'll explain better what these specific values are. There's 5 different types of infiltration. You can do Horton, modified Horton, green amp, modified green amp, and curve number. So you can do curve number for a person who was asking about that. Most people recommend that we use green amp. And you want to have suction head, conductivity, and initial deficit. These particular values are extremely important for accurately modeling the infiltration in SWM. So that's your sub-catchment. Then you go to the nodes. The nodes are the junctions between different portions of SWM. And you can have different values. You want to know your lengths. You want to know your geometry. You can go in with different types of geometry for your conduits. You can use culverts. You can use pipes. You can have, and in fact, in the SWM reference manuals, they have a lot more detail on how this can all accurate, how this can accurately do. I prepare this with circular, so I'm sticking with circular. The routing system, you can have steady flow, kinematic wave, or dynamic wave, as I have said. And when you have dynamic wave, you can have 2 different types of forcing range, the Hazen-Williams and the Darcy-Weisbach. So you want to, so these are the defaults for the project that I've done. I'm going to, I have this prepared just in case I totally screw this up. For map display, I'm just going to tell it to display so everybody can follow what's going on. Alrighty, we're going to start with our system. What I suggest you do is you go from left to right and you go from top to bottom when you're doing a project in SWM. Starting with hydrology, okay, we're modeling storm water, we need to get rain gauge. We're going to put in a rain gauge. The rain gauge needs rain, so we're going to, so we need to put rain into our rain gauge. You can either go to NOAA and to other web places and get historical rain, and in fact I recommend that you do continuous calibration for rain. But right now I'm going to put in just a simple example. I'm going to tell this rain gauge that you should use time series 1 rain, and which I'm going to add next. You also can put in you can put in a time series name, add a description. You can use an external file to put it in, which is probably what you are going to be doing with your real projects. But for the purposes of this demonstration, I'm going to put in a very simple time series. 0. And I have minutes, I have rain, I put in inches of rain for value. And so this is a precipitation curve. So I say, okay. Now going back to hydrology, I want to put it into a sub-catchment. I want to add a sub-catchment. And so I go here, and I can put it in. If I had a georeference figure, I could put it in as a map, and I could click around it, and I could get the area that way. This sub-catchment has the default values that I put in. And if I wanted to change it, I could. I also need to specify for it the range gauge and the outlet, but I need to put them in before I can put in the rain gauge right now. But I need to tell it the outlet, and in order to do the outlet, I need to specify it. So I go to my hydraulics. I go to the node. I put in a junction. And this is a junction. The junction also has properties, which I had specified with them earlier. You'll notice that it treatment doesn't have inflows yet. I will specify that later. And I put in an outfall. Outfall is usually the measurement point that I'm interested in. How many inches of runoff did I get? And that also will have the default characteristics that I put in when I set this up. So I need to connect to my subcatchment, to my junction, and my junction to my outfall. So for my subcatchment, I tell it, the outlet for it is the junction. For my junction, I draw a conduit. I put in a conduit. And I hope we do this right. And so now I have connected my rain gauge to my subcatchment to my junction, and my junction to my outfall. Hopefully, and I have my time series rain, so hopefully I'm able to run a simulation. Yes! Oh, with warning. That's the first time I've done this several times. So SWM will report. Here's my report. Here's what I did. I used the Horton infiltration method. I thought I was using green ant, but anyway, I did the Horton infiltration method. I had dynamic wave. I have my volume. I have my precipitation inches and volume in acre feet. I have my flow routing in acre feet and gallon. I have various different other values of the run. I can graph, if I want to graph something, I can produce a graph, and this isn't very interesting because I didn't have a very interesting rain. So basically what happened is I had flow. As soon as I filled up my flow, I had it outfall. I also can get table, and it will give me the values. And with these, I can use them for various different other reporting values. I mean, you're able to calibrate. You can come up with an actually measured value. You can put it into this calibration data. You're able to calibrate your model of SWM. So that, very quickly, was how SWM works. Now, that's a simple example. Most of you will be doing far more complicated examples than I. In fact, let me give you an example of one. This slide I got from Bob Dickinson from Innovise, and this is a much more realistic. This is probably something that those of you that will be taking SWM output in order to do approve of CSO designs or come up with TMDLs will probably see. This is a animation. SWM does animations, but you need a much more complicated system than what I had. So in this one, this is InfoSewer. It's part of the InfoSwim family that is sold by Innovise as a commercial product. And you have rain falling in, you have conduits filling up. Up here you see the hydraulic head. Here you see the Q flow. Is that, I don't know if Tim or anybody can tell me if this is too small to see, but later you can see this more carefully. But you can see the flow. When you start to see red, you start to see flooding. And in fact, if this were the outfall and you didn't want to see any flow in here, you'd be able to adjust your hydraulic design so that you could prevent combined sewer runoff. So that is a commercial swim. Swim itself will do that animation, but it's much better. It's much more elaborate in InfoSwim and XP Swim and PC Swim. Alrighty, but if you want to get the free swim, the good old EPA, open source, public domain, anyone can use swim, you go to the EPA's stormwater management webpage. If you work for EPA, you can download it, but you're going to have to get Easy Tech or somebody to get it to open up onto your desktop because you probably don't have administrative rights. When you go to the SWIM webpage, I definitely recommend that you do all the downloads, both for the programs, the source code, the executables, and the documentation. And the first thing you want to do is get the self-extracting installation program for SWIM 5.1.012. It's written in C. It's got a Delphi GUI interface, and the most recent version we put up was in March of last year. You also might find, okay, you also want to get some documentation. You want to get the user's manual. You want to get the SWIM application zip file, which has a bunch of different applications that you might find handy as a reference if you're going to be running SWIM. And you want to get the reference manuals. Lou Rossman, in an emeritus position, put together the reference manuals for SWIM. So SWIM is a very well documented code. Not only is the code itself well documented, but the underlying fluid mechanics equations are well documented. Volume 1 is hydrology, sub-catchment, infiltration, precipitation, evaporation. Volume 2 is hydraulics. How do the conduits work, the pumps work, the junctions work. Volume 3 is water quality. What is the pollutant runoff, build up and run off, and how do the LIDs work? When you go to SWIM, Volume 1, say you're interested in whether or not you want to use green amped versus Horton for your infiltration method. In the reference manual, you will see the concepts discussed, the nomenclature used, the variables necessary for the governing equations, the range for the variables, and interpretation of the results. It's invaluable for helping you get started with SWIM, get started or even using SWIM. In addition to that, I recommend you go to the user's manual. Starting page 18 in the user's manuals, and this is exactly how I started. They have a somewhat more complicated but similar problem of SWIM. You put in 3 sub-catchments, 4 junctions, and an outfall and a rain gauge, and you can start to design it. And as you move through the SWIM user manual, it gets more and more elaborate with what you can want to do. Some of my colleagues here in Cincinnati who are starting with SWIM, I recommend they start with just looking. SWIM can do a lot of things. And with SWIM, you want to just do, I would recommend if you start with the sub-catchment, the junction, the conduit, the outfall, and then work your way up with some of the more elaborate things that SWIM can handle. Here is a web page where Bob Dickinson from Innovise has click by click, screen by screen, nothing left to the imagination tutorial demonstration of the SWIM user's manual tutorial. If you get stuck, you can go there. The reason why I became involved with SWIM is because of LID modeling. As you know, for urban environments, you get a lot of runoff. If you can put in vegetative swells or permeable pavement or something to start to get more infiltration, less runoff, and less run through urban environments, hopefully you have a more resilient natural type system. SWIM can model a lot of LIDs, low impact development, disconnection, infiltration basin, rain garden, cistern, infiltration trench, green roof, porous pavement, vegetative swell, and street planters. The way it does this is you go to the hydrology section, you go to the LID control, and then it'll lead you through what you need. This is a bioretention cell. Rain garden tells you the parameters you need. When you go to the SWIM reference manual, it'll give you ranges that one can do, that one can look at. Either you can measure them directly or you can estimate them through the help in SWM. Green roof, infiltration trench, permeable pavement, and so on. It's got pretty good help. It's got information just in time. You get what you need when you need it. You get what you need when you need it. And I find it very, very useful to try to do this. One of the projects that I did with my colleague, Michelle Platts, who at the time was getting her bachelor's in civil engineering at the University of Cincinnati, was an honorary student with me, and Michael Tribby, is we got some LID module. We got people's master's thesis, say Rob Traver's infiltration trench LID design, and we tried to calibrate or test the SWM LID modules. And in general, SWM did a pretty good between 0.8 and 0.9 for our squares and above 0.5 for Nash Sutcliffe, with the notable exception of the infiltration trenches. The infiltration trenches, it doesn't do a good job with lateral flow, and that was something that we need to add to SWM. That's something we probably will add to SWM, is figure out a way to handle lateral flow a bit better. But anyway, we have tested the LID modules, and we have found them to be fairly reliable. We did the individual LID hydraulic calibrations. Now, I don't know if all of you guys, or how many of you saw Jason Bernagros's demonstration of the National Stormwater Calculator. The National Stormwater Calculator is a decision support tool that is designed for somebody, not necessarily a hydrologist or an engineer or somebody like that, but just any person who wants to put a rain garden or disconnect their roof from the sewer system, and they can use this tool to help them get started. SWM is the engine for the National Stormwater Calculator. If you're totally unfamiliar with SWM, I would suggest you start with the National Stormwater Calculator. You can download it and so on with the same fashion of SWM, and it's a good place to help you get started. You can put in your address. For instance, I could put in my home address here. It would give me the lat long, and then it would lead me to the data that I need to do the stormwater calculator. It looks up the soil from the Surgo database, and it gives me the soil group, the conductivity or infiltration rate, and the slope. It also goes to the national weather stations, and it tells me the closest weather stations that are around, and can give me 36 years of precipitation and evaporation data. Most of the data that's in the stormwater calculator started in 1970 and ends about 2002, 2006, certainly I think 2006. We're looking to update that. But this is a good place to get a lot of data, particularly if you want to do a continuous integration. You want to calibrate SWM not to just one rainstorm, but to 30 years of rainstorm. You can export data from the stormwater calculator. It'll also help you, and in fact it was designed to help people put in green infrastructure onto the site. This is a picture of the EPA building. This is a parking lot, and it had some vegetation areas. We went through, we put in a parking lot garage, and if we wanted to start to size, we lost permeable surface area. We wanted to add one of the green infrastructures to improve the infiltration. The National Stormwater Calculator will help us size that. In this particular case, if we wanted to take 70% of the impermeable area and make it porous pavement, we could design it to a 1.59 or 1.6 inch storm. SWM would help, or the National Stormwater Calculator using SWM as its engine would help us size the porous pavement. We can accept or change, or change the permeable pavement, and then the Stormwater Calculator will generate how much good this green infrastructure will do us. The baseline scenario for this case is for Cincinnati, and we get about 40 inches of rain. And if we have a lot of impermeable area, 32 inches of those 40 inches of rain will run off. If we take 70% of the area and put in a porous pavement, instead of 32 inches, we can get 26 inches of runoff. And we can continue to size, add some rain garden, put in a green roof. We can start to see what we can do with green infrastructure. That probably will not prevent us from having runoff, but can certainly reduce the amount of runoff that we can produce, that we will produce. I recommend you take a look at this, this tool. It calculates the difference between a warm, wet, or hot, dry climate change. It'll give you a cost of some of the LIDs that you might want to put into your site. And it's good for anybody, whether you're a professional in the area or not. Also, the other thing I like about the stormwater calculator is it kind of leads you through the data that you need. I did a project in Kansas City. We took 100 acres. We put in rain gardens. I have to say I did a project. I inherited a project with retirement of my colleague Richfield, and we had 100 acres. We put in as many rain gardens as we possibly could, and we measured to see how the runoff changed. We measured soil infiltration. We measured rain. If you don't have it or you're looking at a site where you're just getting started, you can get soil infiltration rates and other topographical information from the SERGO database or the STATSCO database. The land use, what's the percent permeable, what's the percent non-permeable from the National Land Cover database. Climatic data. It wouldn't hurt to use SWM. The stormwater calculator. The stormwater calculator has the precipitation and evaporation data formatted directly to go into SWM. You can also go to NOAA and get more recent information. The most recent information I think I saw was 2013. You can get site configuration like the sub-catchment area and the drainage flow. I usually take a georeference map, put it into ArcGIS, and get areas, lengths of conduits, and so on. If you're looking at conduits and you're looking at storage tanks and so on, you're pretty much at the mercy of the municipality, and you have to get the conduit geometry, length, network schematics. This, frankly, is the hardest thing to get sometimes. The city of Cincinnati uses SWM and spent $1 million on asset management, figuring out where what kind of gray pipe they had in the ground. And then they spent another $1 million using SWM to calculate how they're going to change the infrastructure for the combined sewer overflow consent decree. EPA will accept their design based on SWM results. Alrighty, so here are some web pages for information. EPA Exposure Assessment Model is an excellent web page. I recommend you go to it, as are the NRC, USDA government web page, and USGS has some good stuff. I'm sure many of you that do TMDL calculations do go to the data gateway from NRC, and I find it a very useful place to get a lot of data. All right, for support, SWM was downloaded 33,000 times last year. Michael Trivy, myself, 2 other colleagues are the only folks working at SWM, and none of us are working on it full time. And none of us have had 17 years of experience like Lou Rossman. So there's an excellent group. I recommend you go to openswim.org. This will be the home page, and you join the SWM user group. For some reason, Lou Rossman, Bob Dickerson, Bill James, and a lot of other people who have been working with SWM for 25 years are working by and large in an emeritus situation to help people with technical questions for SWM. Last Wednesday, these were the data. There were 13,531 posts, 4,778 threads from 1,500 contributors. You can put in a question, how do I handle such and such with SWM? And you'll find a chat thread that you can follow that typically will solve most of your problems. I myself go here every day. It's very useful. So here are some of the key websites that I discussed. Here's the stormwater management model where you can download SWM. Here's the National Stormwater Calculator, which I definitely suggest you take a look at and perhaps even start with before SWM. The water research webinar series is here. USGS's online seamless data warehouse. The YouTube videos. In fact, if you have a question and you're trying to solve it, YouTube isn't a bad place to go because a lot of folks have put up stuff. There's things in Arabic, Spanish, French. SWM is used throughout the world, and there are YouTube videos in many languages that are very, very helpful. And of course, OpenSWM. And so the most recent publications, one is NASI from 2017. This is a stormwater management model, performance review and gap analysis. It's a very good reference for looking at SWM, where it was used, how it was applied. You might find where people got data, where they can see example projects. It was put up in May of 2017 of last year, and it's been downloaded 1,339 times as of last Thursday. The testing of the SWM model LIDs, Michael, Michelle, and I are going to be putting on, hopefully submitting to the journal soon. It's under division review. And so with that, I'd like to thank you. I really appreciate everybody coming. And if there's any questions, I can see if I can try to answer them now.
Thank you, Michelle. We do have plenty of time, so we have a good bit of questions that we could go through, and then if you feel like you need to show us anything else, you certainly can share it with the group. And also, there's also a new set of polls up at the bottom of the screen that you participants, if you would go ahead and have a look. Michelle, so when modeling BMPs, are they modeled individually or are they lumped into a proportion of the sub-catchment area?
They're a proportion of the sub-catchment area, but you can make it, what we did is we did end up having a sub-catchment feeding a sub-catchment that was 100% LID. So you can do it both ways, I guess, but the prescribed way in the reference manual is a proportion of the sub-catchment area.
Right, so if I kind of understood what you said, that you would actually make a sub-catchment, an individual sub-catchment for your BMP if you wanted to do it not lumped.
Yes.
How accurate is the dynamic modeling for coastal communities? In other words, you know, how well is SWM working with water surface and dynamic groundwater?
That's very interesting, and that's by next, starting March 1st, I'm going to start working on that. I'm interested in PFAS in the subsurface, and I'm looking at groundwater, surface water interaction, and that's a very good question. I personally do not know. If anyone has a better answer, I'd be glad to hear it.
Okay. Has SWM been used for commercial or residential developments to determine the amount of area that needs to be set aside for BMPs, such as bioretention facilities?
I'm sorry, I missed the very first part. Say that again, please.
Has SWM been used for commercial or residential developments to determine the amount of area that would need to be set aside for BMPs, you know, such as bioretention facilities?
Yes, that is exactly what SWM was designed for, particularly the LID portion of it, which is relatively new from 2010. But prior to that, it was definitely used for that purpose.
Okay, good. What level of urbanization would you define SWM versus ag? Where do you draw the line where SWM would be better or SWAT would be better?
I would use SWM on the urban portion and SWAT on the SWAT portion and interface the two, as did Chris Nietzsche.
Okay, but what happens if we really only want to try to use one model?
Well, okay, what's the most important? Is the most important parameter you're looking at nutrient runoff, harmful algal blooms, you know, surface water interaction? I would use SWAT. If the most important thing is combined sewer runoff or stormwater runoff into a hydraulic system, I would use SWM.
I would say that was a very good answer. Can the SWM model calculate the cost of green infrastructure improvements?
Yeah, not SWM, but the stormwater calculator. If you go to the stormwater calculator, they have a cost module. They looked at various different, we looked at various different cities like Denver and San Francisco and, you know, New York and Chicago and so on, and have various different parameterized costs. If you're going to be looking at your combined sewer overflow consent decree and you're talking about the city of Cincinnati and $2.5 billion in 20 years of work, you're going to want to hire a company and really look at it much more carefully. If you're going to be looking at the back of an envelope, look at the stormwater calculator cost and see how they do it.
Okay, that's good. Does SWM make accommodations for irrigation with reclaimed water? Not
really. You know, it's funny, I have a project that I could do that with, but not directly as far as I know. I could see how one could do it by adding the irrigation water into the time series, or you could use it in having a irrigation water hit a subcatchment and the subcatchment empty into another subcatchment. Not directly as far as I know. I'll look into that some more. You could make it work. One of the things about SWM is if once you understand the principle, you can adjust and you can start to try to model these things. It doesn't, for instance, look at irrigation water and field capacity and see how much you need to do for your soybean crop. That would be a SWOT application, much more so.
Okay. You talked a little bit about buildup and wash-off for pollutant concentrations. Can SWM also do event mean concentrations?
Yes, it can. It can do event mean, exponential, and another kind. I'll have to think about it. Yes, but it does do event mean concentration. And in fact, when you go to the build-off, wash-off chapter, I think it's chapter 4 in the water quality manual, it will describe the various ways it can do it and what you need to know. And I strongly recommend you to put it there.
Excellent. Can it directly model multiple green infrastructure options to assess source flow reduction and reduce CSO discharge volumes?
Yes, it can. As a matter of fact, the stormwater calculator can do that. You can put in permeable pavement and green infrastructure and green roof and surface disconnection and so on. But yes, you can design your SWM model to do multiple. You don't necessarily have to use the same LID each time.
Okay, great. Can SWM model urban snow and snowmelt processes?
Yes, it can. I didn't go into it, but they do have a snowmelt option.
And then just to be clear, the SWM EPA interface is not web-based. It's something that downloads and runs on your machine, correct?
Correct. And it's not an ArcGIS add-in or something, so it's not quite as robust as a lot of programs that use ArcGIS. You do not need any extra software to run SWM. It runs independently.
Okay. These questions are bouncing all over the place, but I think we're doing very well. Does SWM have removal efficiencies built in for different green infrastructure technologies? Sort of have a database of if you use this one method, this is what you could expect to be removed.
Yes. Yes and no. You can, okay, what you can do when you put in your LID, you put in different thicknesses of soil layers and storage layers and so on. This is very well handled in the reference manual, in the LID portion of reference manual number 3. And it looks at, in the reference manual, it talks about literature, it talks about various different removal efficiencies and gives the references thereof. The Platts paper that we hope to come out will go into a bit more detail and more recent references than what are handled in the LID reference. But if you change the thickness and porosity and field capacity and so on at the various different levels, it will give a removal efficiency for it. But you need to, but nonetheless it does, given those parameters, it does have a removal efficiency.
Excellent. Here's a question for calibration. Are you able to link SWM with PEST or another tool?
I hope that's a plan. Yes, we're trying to do that. The Platts paper that I quoted, in fact, that's exactly what we did, is we used SWM and we linked it to LID studies, and we used PEST to come up with optimal values, NAS Sutcliffe, R-squares, and that kind of stuff. The person who was working on that had to leave. We kind of are looking on how we can finish off that project. We have linked SWM to PEST. We do not have a product out there that folks can use. At first, what Michael Tribby did is he wrote some Python wrappers to link SWM to PEST, so it could be done a lot more automatically, but we're hoping to have a product that we can put on the SWM webpage to link SWM to PEST more directly.
Great. Would SWM provide a defendable estimate of peak stormwater runoff for an undeveloped catchment covered with forest and or shrub vegetation?
Well, in the NASI paper, you can see some of the studies that were done for that. It does. It does look at land use. It could have 100% forested or meadow or some other kinds of land use covers, and it will produce a result. How well it does, one would look at the. I would suggest you look at the NASD paper in 2007 and see the studies that covered that. See how well they do. All of this stuff. One of the things I'm one of the few people in the modeling community who really looks a lot more at testing of models in addition to the development. You want your model to be fundamentally sound. You want to have the physical, anything that you can measure physically to put in as an input to the model you want to do. And I also want to test the model. I used to say validate, but Steve cautioned me on not saying validate. But you definitely want to calibrate and look at how accurate your model is. And that's true for anything, SWOT, HSPF, or whatever, ModFlow, anything you use.
Okay. Here's a question that always leads to frustration whenever I have to use a watershed model. What format is the rainfall data in?
That's a very good point. Date, inch, or date, millimeter. And you need a, yeah, I could, in fact, if you go to the stormwater calculator and you export the data, you can see exactly what the format will be. It is not the format, and I understand your point, Tim, about the frustration. We spent a lot of time reformatting NOAA data into SWM data. And in fact, for the stormwater calculator, we have it sitting on the web page. One of the things we'd love to do is go and to get NOAA data on the fly and put it into SWM, and we found that to be too hard to do with the first method that we tried, and another one of my students, Colleen Barr, who was doing some fantastic work for me, is looking at how we can do that. That's non-trivial, getting your data in the format you need into the model you want to use.
Yeah, I would suggest, and this was suggested about 25 years ago, that we come up with a standardized file format and have all of the models that are driven by meteorological conditions use the same format.
I wish they had listened to you 25 years ago.
Okay, can the model channel route within the basin or identify an outlet within the basin based on the channel in that basin?
Okay,
So,
if you have a sub-catchment, the rain falls in the sub-catchment. The sub-catchment is routed to something, a culvert, a conduit, a junction, or something. Okay, I guess it's to a junction to a culvert. But anyway, you can break up your basin however you want, and you can route it however you want. You don't have to have the entire watershed as one sub-catchment. That's the trick for SWM.
great. Does the model allow for non-structural BMPs, things like street sweeping and other practices?
Yes, it does, and it does in the contaminant buildup, and the dry buildup allows for street sweeping.
Okay. Can SWM model a detention tank and an outlet control system?
Yes, it can. In fact, I think there's an example of that in the user's manual.
Here's another good question. Do you have any guiding documents for the calibration in general of SWM?
No, I do not, and that's an excellent question. The Kai Water people, you know, one of the vendors, they have a document on modeling. And at first I was going to give it to you, but it's a bit out of date. It's a bit, let's see, Lou Rossman, as a matter of fact, when I ran my slides through him, he suggested I not recommend it to you. If you go to, you know, how to calibrate SWM in Google, this document will come up, but it's a bit out of date. It's a bit, according to Lou, a bit disorganized, and that would be a lovely thing for somebody to do.
Great. Okay, so here's a geek question for you, but could you talk a little bit about SWM, its model time step, and how that model time step fits into curve number calculations and infiltration?
Okay. Whoever asked that is a true geek. Okay, and this is covered very well in the first reference manual. You start off with an initial time. You go up a time, and in fact it talks about like time step and courant numbers and how you want to keeps swim from, being stable and not becoming unstable. All of this is very smoothly handled in the reference manual in the first part. Let's see, and it's a Newton-Raphson, solver. It's I think I'll just leave it at that. If everybody's really interested, let me see what I can show smoothly. I thought somebody might ask that question actually, and so I sort of prepared something. But why don't I just leave it, because I'm not sure how interested everyone in that group is on, check out the very first reference manual, because it talks about time steps and how you figure out what they should be in order to keep the model stable.
Yeah, I mean, the underlying principle there is you have a curve number that's based on a longer time scale than your time step, and how does the model account for that as it's taking an hourly time step or so. But yeah, we can't answer that question here. This one might put you on the spot a little bit, but it says, how do you model sediment transport from, I think it's the stormwater calculator.
Oh, it doesn't do it at all.
It doesn't do it at all, okay.
It doesn't do it at all. It's strictly hydrology.
Okay. Does SWM allow the user to simulate water temperature or use water temperature as an input?
I don't think so. No, I don't believe so. For those of you that are really interested, here you go. But no, I don't believe it does water temperature. Now, does it do it for snowmelt? It does evaporation. I don't believe it looks at temperature, but if I'm wrong, I'll do an errata after this.
Okay, actually, I don't know the answer either. I've used SWM a bunch, but I don't think it does. I don't think it predicts water temperature.
It does. It needs temperature for evaporation.
Right.
For those of you that are super interested, here you go. Okay, but for I would say no. Does WAS do it, Tim?
Yes. But if we were linking, to SWM and we were taking runoff from SWM, we would expect to get water temperature of the runoff. HSPF, LSPC, SWAT all predict water temperature as well.
Mm-hmm. Okay.
Okay, here's a question. We might have confused a couple of people, but they want to know what is the difference between EPA SWM and open SWM?
Okay, open SWM is run out of the University of Guelph, and which is in Canada, and I may not be saying the name correctly. And open SWM is for the community support. SWM has, I don't know how many folks here have been looking at modeling and development of models, but there's something called the cathedral and the bazaar. And SWM at first was a cathedral. EPA and then a couple of cooperative agreeers like CDM Smith and Kai Water and so on developed SWM, and EPA releases a free, open source, public domain version of SWM. In open SWM is a community, and people who do it are people who are interested in SWM. They're not paid. They're not a contractor to the EPA, and it's not just the EPA. It is, let's see if I can get this from current slide. Okay, and so people will donate code. We'll talk about, why isn't this working? Okay. I'm not sure why this isn't working. So anyway, for Open SWM, it's a community, and people will have questions. There's a listserv. There's a community. People will have differences in code. If I can figure out how to do this, I'm going to change my figure here and show you how it is. And people put Python wrappers. There's an API toolbox. There's a bunch of stuff. The people who develop it were not necessarily the EPA and are not necessarily contractors to the EPA. It is a different group of folks. And for those of you, I don't know how familiar folks here for it, but EPA is going to be heading in that direction. Instead of having all the development for SWM, EPANet, and other kinds of software only in-house, they're going to be using community and accepting code from the community, and they're going to be using things like Bitbucket and the GitHub process so that they can look at source code.
Okay. Does SWM use the NL- meteorological data?
Not directly. You're going to have to take the data and put it into the format for SWM.
Okay.
Same as the precipitation data. One more thing, if I may. See the swim code viewer that's in the OpenSWM? OpenSWM is run by, volunteers. Nobody paid by the EPA. However, people like myself go to it all the time. The swim code viewer will let you look at SWM. It'll look at EPA SWM versus the products sold by PC SWM, XP SWM. There's a bunch of folks who are doing various different ways for SWM, and some of them are strictly the SWM engine, and some of them there are other embellishments to SWM that are not put into EPA SWM at all. And advise you to look at the swim code viewer so you can look at the differences between different kinds of SWM.
Okay, we only have a couple more questions here. Can you talk a little bit about where sustain is and how SWM is coupled into it or not coupled into it right now? Okay,
sustain is a decision support tool that helps the user evaluate the cost effectiveness of various different hydrological improvements to a design. It uses SWM as an engine. Tetra Tech was the developer for sustain and was a contractor to the EPA for 10 years. Sustain was an added into ArcGIS 9.3. When ArcGIS moved to 10.x, this version that EPA had of sustain no longer worked, and we would need to figure out a way to upgrade sustain to work with ArcGIS. We decided not to make sustain an add-in for ArcGIS, but to decouple ArcGIS and sustain, and it can work back and forth. And you can go to the sustain EPA sustain webpage and pick it up, and it's there. We are no longer developing sustain. However, Tetra Tech, Innovise, Paradigm H2O, and several other vendors are selling sustain, and you can either use the last version that EPA produced, which I think was in 2012. You can get the open source code and use it yourself however you like, or you can go with these companies and they can, if you feel that you would like to use it, and use their expertise.
Was funded by EPA.
Okay. Great, Michelle. That's it for the questions right now. Great presentation. We did not try to answer all the questions. If you have questions, feel free to contact Michelle or myself, and we'll try to get you the answer the best we can. So with that, just a couple other things that we have to go through here, and then we'll conclude the webinar. And again, if you haven't completed the poll at the bottom, please do so. If you want to get a certificate for attending this webinar, you use this link below. To find out about additional webinars in the future, you can always find them online, as well as the recorded webinars after they're posted. Okay, our next webinar is actually going to be on March 8th, I believe, and it's going to be on the WMOS version 4. So visit the water modeling workgroup webpage for future details about this webinar. This webinar will be, the webinar we just completed will be posted on the water modeling workgroup webpage, hopefully within a month. The link is on your screen. So at this time, I want to thank Michelle for, that was a great presentation and handled the question and answer session very well. I encourage people to contact myself or Michelle in the future if you have further questions. With that, I'm going to end this webinar, and I want to thank everybody for attending.
Thank you, Tim, and thank you everybody for coming. I really appreciate it.